All right, this video is going to talk about solving trigonometric equations when we're dealing with what I like to call looping, when we're dealing with a multiple angle. Noticing here we've got the secant of 3x, so no longer just x, like we've solved most of our equations probably up to this point. We're actually the secant of 3x. And again, I'm going to take those parentheses off just because they get in the way a little bit there. But secant of 3x. Now, imagine that it's really just an angle. It's just a multiple angle. But I'm going to put that parenthesis back in because really that's just one simple angle. So I'm going to approach this like I normally would. I don't really like thinking about secant, but I know that the secant is 1 over the cosine, right? Therefore, 1 over the cosine of 3x. So if I take its reciprocal, the cosine of 3x should be equal to, well, the reciprocal on the right, negative 1/2. Well, cosine of an angle, any old angle, I'll get to that 3 in a minute, don't worry, but the cosine of an angle is equal to negative 1/2 at both 2 pi over 3 as well as, again, cosine's also negative down in quadrant 3, right? But if I think about my side lengths here, remember that this was always negative 1, positive root 3, and 2. So negative 1 over 2, adjacent over hypotenuse, at 2 pi over 3, and also down here at 4 pi over 3. So two of our possible answers, right, would be 2 pi over 3 and 4 pi over 3. However, remember, that's just the answers to the cosine of an angle equals negative 1/2. We're still equal to 3x right now. And if you remember on a graph, if we graph the secant of x, 2 pi is the period of the secant, right? 2 pi is the period of the secant. But if we take the secant of 3x, remember multiplying by 3 is actually going to shrink the period by 1/3. So the secant of 3x is actually going to happen 3 times over before we ever reach 2 pi. Which means if I say, when is that equal to negative 1/2? Well, negative 1/2, or sorry, negative 2 for the secant, right? Negative 2, there we go, is going to be down here. Right? And we're actually going to intersect, by the time we get to 2 pi, this would be, or these would have been the first two answers we found, but we should actually find 4 more answers. We need to shrink this down. Or if you notice, the last thing we're going to do is we still need to divide by 3. So I still need to divide all of my answers by 3. The problem is I don't have all the answers yet. I only have 2 of them. Because by saying 3x, what we're really doing, and this is why I call it a looping problem, is we need to consider going around the circle 3 different times. 3 separate times. So I got my first 2 answers, right, by traveling around that first full loop. But again, the next 2 answers come from traveling around again. Or basically saying 2 pi over 3 plus another 2 pi, or 8 pi over 3 would be a possible good answer. 2 pi being equal to 6, right? Pi over 3. And if I take 4 pi over 3 and add 6 pi over 3, right, that'll get me this second answer over here. So 10 pi over 3. And again, those would have been the third and fourth answers down here on our graph. Finally, let's go ahead and go get our last ones. Let's go one more loop around. Again, I'm going to add another 6 pi over 3. So that would be 14 pi over 3. And 16 pi over 3, because now I'm going to divide all of those answers by 3, or basically multiply them by 1/3, and we get answers of 2 pi over 9, 4 pi over 9, 8 pi over 9, 10 pi over 9, and the largest ones, 14 pi over 9, and 16 pi over 9. Which, if you think about it, 18 pi over 9 would be 2 pi. So if 16 pi over 9 is less than 2 pi, so are all the rest of those. And I'll leave it to you, but I guarantee you if you plug any one of those answers back into your equation, it'll make your equation true. All 6 of those between 0 and 2 pi, right? We haven't exceeded 2 pi yet. All 6 of those are answers to our equation. Let's take a look at one more looping problem just so we can kind of see how this works one more time. So I'm going to go ahead and click over to a new example here. Now notice this time it's pi or x over 2. It's not times 2. Well, if we divide by 2, remember that's like stretching horizontally. So it's actually stretching the period of the tangent. So instead of the tangent having a period of pi, we're going to stretch it by 2. The period, right, if we were thinking about this as a sort of periodic graph, right, we're thinking about tangents, so it's going to kind of curve up and through, right? The period of this graph is essentially going to be a width of 2 pi right now. Normally it would have been pi, but again, we're going to call it 2 pi. Therefore, from 0 to 2 pi, right, if this is going to be pi units right here, again, we would be another sort of half a tangent here. But we're not going to look at this side. We would essentially want this part of our graph, right? Which means we're really only likely going to be equal in one place, right, wherever we're looking. So let's go ahead and take a look at this. And again, you don't necessarily have to draw out the tangent, because watch what I really do. Let's subtract 3 and divide by 3. So I'm going to start by subtracting 3. The tangent of x over 2 equals negative 3. Divided by 3, that means that we're equal to a negative 1. Then we would take our inverse tangent, or we would imagine on our graph, when is the tangent equal to negative 1? Well, remember, the tangent is negative in quadrants 2 and 4. And at exactly 45 degrees, or basically at 3 pi over 4, and at 7 pi over 4, we would be equal to negative 1, right? Again, if we think about those side lengths, opposite over adjacent, right? Or if we drew that triangle, the opposite over the adjacent, 1 divided by 1, as long as there's a negative in there somewhere, that's going to be a negative 1, right? Only now, that means that x over 2 is equal to 3 pi over 4 or 7 pi over 4. And I'm going to multiply by 2, right? Because I need to get rid of that 2. I'm going to multiply both of those by 2, which means that x equals 3 pi over 2 or 7 pi over 2. Well, the problem with 7 pi over 2 is that's greater than 2 pi, which means that that's not a good answer to our equation this time. And our only good answer from 0 to 2 pi is going to be 3 pi over 2. Now that makes sense because, again, x over 2 tells me not to take multiple loops like I did on the last example, right? Remember on the last example, we multiplied by 3, so we took 3 loops. Well, in this example, we're dividing by 2, so we only want a half of a loop, right? A half a loop. Kind of a Winnie the Pooh thing, right? Half a lump, half a loop. Sorry, bad joke there. But again, first half loop on our unit circle would only intersect this one angle. I hope that helps you with those looping problems. If you ever have a problem where there's tangent of or sine or cosine of x either divided by a number or multiplied by a number. Again, that's a multiple angle problem, and we can definitely solve them, but take advantage of the looping idea and see if that helps you out. If you need any help with any of that, make sure you talk to your teacher. Otherwise, good luck, have fun, and have a great day.